commercial satellite providers are producing somewhere between 100 and 200 terabytes of imagery a day. That's a monstrous amount of information.
Welcome to another episode of the Mapscaping podcast. My name is Daniel, and this is a podcast for the geospatial community. My guest on the show today is Simeon Fitch, and he is the VP of Research and Development at a company called Australia. And today on the podcast, we're going to be talking about an open source geospatial project which Australia sponsors, and the project is called Raster Frames. So Raster Frames is an extension to the Apache Spark environment, and right at the start of the conversation we give you a brief overview of what the Apache Spark environment is, and then sort of move on to talk about Raster Frames and how it adds geospatial functionality to that environment, specifically focused on imagery. A really big thank you to OSGeo who helped make this podcast possible. I really appreciate your support. Thank you very much. Hi Simeon, welcome to the podcast. I really appreciate your time and the fact that you're taking the time to teach us all a little bit about Raster Frames today. I think before we jump into the conversation around Raster Frames and of course Apache Spark, it would be really useful for the listeners if you could just take a couple of seconds to give us a brief understanding of your background.
Sure, it's nice to be here. My background is really as a software engineer. I'm a little bit of a black sheep in the GIS space, perhaps. Most of my career has been spent working for engineers and scientists, helping to build tools that they need to make them more efficient, more effective at what they do, and to also help take any kind of scientific or engineering innovation that they've created and turn it into a commercial product.
Okay, so you come at this from a software engineering perspective, and right at the start there, I mentioned something called Raster Frames and Apache Spark. I think perhaps because Apache Spark is the environment that this Raster Frames lives in, perhaps we could start there. What is Apache Spark?
Sure. Apache Spark is a framework or a foundation upon which big data applications can be built. And it's lots of things to different things to lots of different types of people. For some, it is a data engineering tool used for processing large volumes of data on a regular schedule. For some others, it's an analysis tool for doing interactive exploration of data. And it's doing all this in a format or a construct that allows you to take the work that you're doing, perhaps starting off on a laptop, and then deploying it to a larger compute infrastructure, say a cluster. And so it's what we call horizontally scalable.
Is this the concept of distributed databases?
It talks to distributed databases. It's more the concept of distributed computation. The way I like to think about it is imagining you taking the work that you're doing on your laptop and then doing it with a small amount of data, and then saying, hey, I want to do that same operation, but I want to do it on so much data that it won't fit into my computer. And Apache Spark gives you the ability to do that without reconstructing or reformatting the way that you've expressed your computation. So, for instance, if that were to go and count words in a document, you could imagine writing some software to do that locally on your laptop. But then if you wanted to count all the words in Wikipedia and monitor the number of word changes over time, you could imagine that might be a larger compute job for your computer. And therefore, something like Apache Spark allows you to harness the power of larger compute infrastructures without necessarily being an expert in distributed computing.
Okay, so it sounds like the magic here is that I don't have to rethink my logic in terms of programming I've done, the algorithms I've created. I can just pass all this over to Apache Spark and it'll figure it out and transform that into the way it should be on a massively parallel environment.
Yes. Those are the ergonomics, what we call the ergonomics of it. We're trying to, and that's why we picked Apache Spark as the foundation for Raster Frames, is that we were looking to provide tools for people who wouldn't normally have access to, say, a huge engineering team to restructure their analyses to work in a cluster environment. Apache Spark provides APIs that are both friendly to data engineers, so software engineers who work regularly to restructure data for other people to analyze, as well as people who are, I use the generic term analyst to mean anybody with some sort of quantitative background, whether that be a cartographer, or an environmental scientist, a data scientist, a machine learning expert. Apache Spark, with its what we call Apache Spark SQL, its SQL interface on top of that provides a unified SQL and data frame view into your data, into your compute job.
I love the fact that you talked about friendly APIs. This is a concept I think we need to talk a lot more about later on. But
yes.
So you've given us this, well, I think it's a really good sort of overview of what Apache Spark is and what it can do for us. I'm sure there is a lot more, but I really want the focus of this conversation to be around raster frames. So we understand a little bit more about the environment now. Can you tell us what is raster frames?
So RasterFrames is, at a technical level, it is making geospatial raster data and vector data first-class citizens within the Spark ecosystem. Spark in and of itself is sort of agnostic as to the type of problem you're going to solve, and is, geared towards to sort of typical business analysis or just scalar data analysis. Geospatial data is interesting and a little bit more challenging because without a unified interface over it, as we provide with raster frames, you're having to deal with some very kind of technical and esoteric constructs that are extremely important for the purposes of managing the data. But as an analyst who's looking to measure something about plant health or to detect changes in a construction site, those are all problems where you're having to deal with the bookkeeping of tracking, okay, when was this raster taken? Where is it? Where on the planet does it exist? What sensors were on or were used in creating the image? All those sorts of things we attempt to manage and do the bookkeeping throughout the analysis inside raster frames, and only expose it when the user either asks for it or it's absolutely necessary for the user to have to think about those things. We try to keep the focus for the analyst on the data that they care about and on the type of processing that they're looking to construct.
Okay, so let's imagine for a second I have some geospatial data, I have some satellite data, for example, and I push it into Apache Spark, I push it into raster frames, and when I'm doing that, raster frames takes care of all that geospatial stuff, and it becomes data. It becomes perhaps a data frame, so a multi-dimensional array of data. Is that the kind of understanding I should have?
Yes, and if I would like to extend the analogy even further. So first of all, yes, raster frames is a data frame with geospatial raster data in it. And what that means is a data frame, I like to say, is the lingua franca of data scientists. It's a tabular structure. You can think of it as a database table because it's interoperable with SQL and can be seen as a database table. But I like to think of it as a really large spreadsheet where the data on a particular row of a data frame is a specific place on the planet, a specific point in time, and the columns can be thought of as different layers on a map. And so what that means is take that spreadsheet, you can do operations across columns and aggregations throughout the rows, say compute, average luminance for a location, or when it's across a row, you can combine bands to create, say, take the RG and B channels of an image and combine them into a composite of some sort. And so imagine that spreadsheet then being able to be stretched out across multiple computers. Now you're starting to understand how you can think about it as a small table or a small spreadsheet, but in fact, it's actually being distributed across a lot of compute hardware.
This all sounds really exciting. I just want to go back to this idea of bookkeeping because, when we deal with spatial data, we have things like, and you mentioned it before, what sensor did it come from? What resolution was it? What coordinate system or is it saved in? And when I think of bookkeeping, I think of taking care of all of these things. And when I think of having real benefit of using different geospatial data sources, I think someone needs to do this bookkeeping. Does this all happen for me in raster frames?
We go to extreme lengths to try to make that so. So for instance, let's say you have one raster frame that contains data over a city at one resolution, and then you have another data set at a different time over the same city, but it's a different resolution. You can imagine trying to get those two tables merged together, or as a join, as we call it, and having each of those rows represent the same place on the ground. Well, to do that, you have to ensure that the alignment of the images on both of those tables or raster frames is the same, and that the resolution is the same, so that that row that results from the join is coherent with respect to space and resolution. And so what we do is with each column, we actually have a bunch of metadata in there that says this row it corresponds to this extent or this area on the planet. It is that extent is encoded in what we call a CRS, which any GIS nerd will know about. But it's the way that those pixels are projected onto the planet, onto the surface of the planet. And when you join two sets of disparate raster data, they all need to line up. So a pixel on one covers the same area as a pixel on another. And so the metadata that we encode inside these columns helps us do all that automatically and keep track of what is the resolution, what is the CRS, what is the extent, so that the user can just focus on, okay, I'm just interested in this place on the ground, and here's what the sensor is telling me about that place on the ground, and do the bookkeeping for me, but don't take it away from me. So if I do want that information, you can always ask for it and get it out of Raster Frames.
So please correct me if I'm wrong here, but once we have pushed our raster data into Raster Frames, it takes care of the bookkeeping, and we can start to think of it instead of imagery as almost tabular data, right? So rows and columns, I think you described it as before. Does that mean that I can start to fuse data sources? So if I have other data sources, other tabular data, other rows and columns of different kinds of data, can I start to join these in the same way I would do joins in a SQL database?
Absolutely. And that's like the first thing somebody tries to do after they successfully load in an image is they want to combine that with some other data. Because, so for instance, if you had soil samples, data, or you had building footprints, or you had census data, any kind of data that has a spatial component, meaning, it's mapped to a place on the ground, we can do what we call a spatial join. And so we know where the image on the planet was taken, and we have this other, and that's in a table form. And we have this other table that contains what we call our vector data, which is a polygon with a bunch of attributes associated with it. And you can do a spatial join with those using operators that are similar to what you might find in PostGIS. So things like ST intersects or contains or overlaps, all of those sorts of geospatial predicates are available in Raster Frames.
Right at the start of the conversation, we talked about we could do this on a laptop. So, deploy our algorithm on a laptop, get something that works, and then scale it up by sending this over to Apache Spark and Raster Frames. And you just talked about SQL there before. Is there other languages that I can use? Because I'm thinking geospatial professionals, we use a lot of different languages depending on what tasks we're trying to achieve. Is this an SQL only solution?
No. So that's one of the benefits of building something on Apache Spark is they provide you the infrastructure to deploy these capabilities in multiple languages. The one we focus on the most is Python. The underlying implementation is actually in a language called Scala, which runs on the Java virtual machine. And so you can write your jobs in Python, Scala, Java, and SQL. So you can treat a lot of the operations as just functions within an SQL query.
So a lot of people when they make things like this, often we hear the term democratizing. We're democratizing access. We're lowering the barriers to entry. And I'm a little bit curious here because some people might hear that as dumbing things down. So geospatial professionals might think, oh, well, what's the point in running around calling myself a geospatial professional if things like raster frames are going to show up and sort of negate my knowledge, my understanding of geospatial concepts. Are we dumbing things down, or are we just getting out of the way of people trying to do science?
Our goal is to just get the minutia, the plumbing, the bookkeeping out of the way of the science. And so I would argue, or most of my my users are data scientists, and there's a commonly known adage that most data scientists spend 80% of their time cleaning data and only 20% doing modeling and analysis. Modeling and analysis is what they really want to do. They don't really want to clean data. And so, in that vein, any kind of improvements that we can make to the ergonomics of working with the data, automatically handling the bookkeeping, helping them to assess the quality of the data, is time that they can then redirect to spend on modeling and analysis. And so a professional with highly specialized degrees, we're not taking that job away at all. They're the ones that understand how to interpret the data. What we're trying to do is provide all the tools for them to manipulate and transform that data in the context of the science or expertise that they're trying to apply to the data.
Thank you very much. I really appreciate you taking the time to clarify your thoughts around that. It's much appreciated. In a previous conversation, we talked about some of the other things that Apache Spark offers. So one of the things was streaming, batch processing, and interactive compute. Could you tell me how that relates to RasterFrames, or perhaps give me some use cases? And I think this idea of interactive compute is really fascinating.
Yes, so that was another. So if you look at why is there raster frames? Why did we create that? You kind of have to start with the who, and the who is we wanted to back to the democratization question. We wanted to make this data available for processing by people who are quantitatively oriented, but might not know about the intricacies of CRSs or extents or cell types and other things like that. The part of the process of developing a model or doing an analysis is exploring the data that's there. What do I have to work with? What is its quality? What kind of distributions does it fall under? And to do that, particularly on quote unquote big data, can be hard. You don't want to have to launch a job, a batch job, meaning a job that runs kind of offline while you're out getting coffee, just to find out what kind of cloud cover you might have over this small area of something. You want to be able to interactively query and say, what if this? What if that? What if I combine this other piece of information? And so interactive computing is sort of similar to what you might think of as a REPL interactivity, REPL being like a command line tool for typing in a language like Python, say, or SQL, where you can type in the commands to say, do this analysis, do that analysis. How about transform it in this other way and do it such and such, until you find out, okay, for my analysis, I need a little bit of A, a little bit of B, and a whole lot of C, and work out the mechanics or the routing or transformations of that data to get to your analysis. You can do all that interactively to figure out or explore or experiment with different ways of doing it. And then once you've settled that all out, you can scale that up and run it in a batch job that might take, if you're doing it over a very global scale area, maybe that takes hundreds of computers or tens of computers and hours of compute time. So it works in both modalities. A lot of tooling out there only works in one of those well, and Spark does a great job of working both in interactive and batch, and it also has a streaming capability, which we've not yet introduced into Raster Frames.
So does that then mean for Raster Frames that I can push all of my, let's say again, satellite imagery into Spark, into Raster Frames, and then work with it in this interactive mode? So I could make my function in let's say SQL and basically just look at whatever was in the window, what was on the screen, and then pan around and have that function automatically executed each time the data was updated, and sort of do this rapid prototyping. Does it make sense here? Does it make sense in an area with different geographical features? Just as an example.
Yes. Conceptually, that's exactly what we're aiming for. It's the ability to solve the problem in the small, but execute it on the big.
That sounds fascinating. And I think this is kind of the future as well, like in terms of getting things done quickly, right? Like finding out, does it make sense? Does my function, does my algorithm make sense in these different kinds of environments quickly? I think this is a really exciting thing.
Yes, it's it's kind of pertinent to one of the analyses we did with Raster Frames in some of our tooling at Estrella was finding utility scale solar farms across the planet. And so originally we trained our model in the United States because there's really good data about in the United States. And so training means we go and find locations that are definitely solar farms and areas that are definitely not solar farms, and feed them to the machine learning algorithm to say, find things that look like this, for instance. It worked, we got it to where it was working really, really well in the United States. And then we redeployed it to Brazil and China and some other places. And depending on what region it was in, we would get false positives. Interestingly enough, radish farms, for some reason, triggered the algorithm. So we then could go to those locations and pull out a bunch of radish farms and say, if you see this is not a solar farm. Or other agricultural locations where there's the tilling in the ground maybe creates a grid-like structure that can throw off the algorithm. And so that's the other benefit here, is you can iteratively evolve the algorithm, do it in a way that's reproducible. If it ran over the United States, just shifting it to another place in the world is just a matter of changing that window that you were talking about.
That is really interesting. From a previous conversation, another thing that you talked about that I found incredibly interesting was this idea of chipping. So this is, as far as I understand it anyway, this is something that is built into raster frames. Would you mind describing for the audience what chipping is?
Sure. Chipping is the process of carving out little small samples of usually geospatial imagery, or usually imagery. It doesn't have to be geospatial, but it's regularly sized squares of imagery of certain things that you're either interested in or know what they are and need to use that to train a model. So they're chips in the sense that they're little carved out chunks of data of a regular size.
So when I first heard about this, I thought this would be a pretty amazing way of building a machine learning training data set. So immediately I was thinking, well, we could go to something like OpenStreetMap, perhaps extract all the polygons that represent tennis courts, just as an example, and then point that at a aerial imagery database and say, hey, go there, chip that data set for me, extract all these areas that fall under the tennis court polygons, and in that way build up a training set for a model. Am I on the right track here? Is this a valid use case for something like chipping?
You're absolutely on the right track. That's exactly one of its strong suits. So Raster Frames, we attempt to base things on standards as much as possible. And one of the standards out there is, well, there's an image format called a GeoTIFF, which your listeners will probably be familiar with. There is a way of formatting a GeoTIFF that falls under a recent standard called a cloud optimized GeoTIFF. And what that is a GeoTIFF that has a certain internal tiling to it it's prescribed, and a certain number of zoom levels within that. And structuring that file in that way allows us to do what we call range reads, or another way of looking at it is saying, I have this big, 10 gigabyte file, but I just want this little corner of it. I want 5 chips over in this one corner of this. I don't want to have to download the whole 5 or 10 gigabyte file to do that. I just want those little bits of data. And so what Raster Frames provides you is the ability to say, I want chips in this small region, go get them for me. And Raster Frames attempts to pull out only those pixels that you need, saving you a lot of network bandwidth and just time extracting that information. And so if you imagine, hey, I want to go find all the radish farms in America, you don't want to have to download regions or whole images that might have a whole bunch of stuff that's not useful to you. You might go to OpenStreetMaps and say, give me all the farms, in an area that might have radishes, say. So it's a huge benefit in terms of chipping, is that it allows you to just download or fetch the data that is relevant to your machine learning model or the type of analysis you're doing, and get you to an answer much more quickly.
And am I correct in understanding that those chips would be returned to the database, to the environment, as a data frame, so not as an image, as a tiny little image, but as a data frame that I could immediately integrate into whatever else I was doing?
Absolutely. So there's 2 ways of kind of doing it. Is you could fetch those chips and feed them directly into a machine learning training or scoring or inference model. Or you could go and read those chips in, do some tweaking to them, normalize them, do whatever you might want to do, and a standard sort of ETL processing for machine learning, and then save that off as either individual small geotiffs, or you can save them off into a big data format such as Parquet for subsequent analysis later.
I just want to stay with this with chipping just for a second here, and I realize we're getting down to the details there. But can I also point this at, say, a tiled map service and say I'm interested in chips in these different areas at these different resolutions? And I guess the next step in my thinking was if I can do it at different resolutions, so build up signatures of these areas, based on different resolutions, which I think might be interesting for machine learning models. Can we also do it over different time frames if the API, if the endpoint allows for that kind of querying?
Absolutely. It's so with respect to the tile server use case, tile servers are sort of an optimization around not having to render your vector data all the time. And so in an analysis, we would typically encourage the user to use vector data first if they have vector data, because it's of arbitrary resolution. But that said, regardless of what the source of the raster data is, it typically has some sort of temporal component to it. And from the perspective of raster frames, that's just another column in the table that says what is the date that this date time that this raster is associated with.
So I think you've done a really amazing job of sort of walking us through Apache Spark as the environment that Raster Frames is built on top of or into, however you want to visualize it. Some of the capabilities of Raster Frames, so what we're getting with it when we say yes to Raster Frames. I really appreciate you walking us through some of the use cases. Really fascinating, especially the use case around shipping. I'm wondering, is there anyone who Raster Frames is not for? So sometimes when we talk about things, we often say, you can do this, you can do that. But for me anyway, it really helps to clarify what it is if we talk about who it's not for.
Sure. I'd prefer to say what is it not for rather than who, because I don't want to presume the types of problems people want to solve. But it's not a tool for, say, making maps. Okay, so it's not a replacement for Esri or QGIS. It's not a replacement for cartographic tooling. This is a quantitative analysis tool, and is focused on, while you can create map layers, it's not its strong suit. But if you wanted to prepare the data in a format that then you could create map layers with, it's excellent at that part of the processing chain.
So again, from a previous conversation, we talked about geospatial data being the next big data set. And one of the reasons I remember you saying you built Raster Frames was to help solve these problems that are either here now or coming down the line at us. Could you talk to us about why you think geospatial is the next big data set?
I would actually argue it's already a near and present big data set. The commercial satellite providers are producing somewhere between 100 and 200 terabytes of imagery a day. That's a monstrous amount of information. There's also the governmental agencies who have, Sentinel-2 has 5 years of daily refresh data. We have 40 plus years of Landsat data. It's a monstrous amount of data, particularly in the temporal dimension, where you can do these longitudinal studies over. I mean, what other data set that goes 40 years back do we have? And it's probably full of untapped capacity or information in there, but we've not until now had the capacity to scale that up to a global perspective without a significant amount of engineering effort.
And this question kind of follows along from that last question there. Where do you think we are in terms of the hype cycle, the hype around remotely sensed data, Earth observation data?
Well, it's going to be, first of all, it's going to be, depends on who you ask. I think for an environmental scientist or an urban planner or somebody who has been using geographic data for decades, this is just a great new data set, or a data set that they're already working to incorporate into their analyses. Now, if you're talking about how does a large Fortune 500 company monetize this data, that's where we as a startup at Astrea are trying to find handholds to get to exploit that. So there is, I would argue that we are sort of on we are in a a piece of the hype cycle, perhaps coming just out of the trough of disillusionment, if you're familiar with the Gartner hype cycle. But it's really starting to, for those people who are progressive in their business thinking, are starting to see how just through some simple integration of raster data, they can take tasks that might have required lots of regular manual labor to say in energy applications, easement monitoring, or do I have plant growth encroaching upon my power lines, or do I have some rogue person trying to build a house on owned property, say? Those are all problems that I think we're just starting to see come up out of the industry and will soon be strong contenders for good business use cases.
So I just want to clarify for the listeners that aren't familiar with the hype cycle. So it starts off with an innovation trigger, goes steeply up to the peak of inflated expectations, drops down to the trough of disillusionment. And you were talking about before, or mentioned before, that you think we're coming out of the trough of disillusionment and we're moving on to the slope of enlightenment and then heading off to the plateau of productivity. What is going to have to happen to RasterFrames, or I should say, perhaps, what is it going to look like when we get to the plateau of productivity?
I think what it's going to look like is really part of the goal of RasterFrames is to make the raster imagery look like just any of your other type of data. Meaning, if you're a corporation and you're analyzing your accounts data, your transactions, or your sales data, those are all different types of data, but the tooling is sort of agnostic to what the contents of that are. It just provides you the fundamental operations to manipulate it, combine columns, do statistical analysis, those sorts of things. Well, RasterFrames is adding those capabilities, particularly through a concept known as map algebra, which is the fundamental constructs for saying, hey, I want to measure the distance or compute the distance or difference between these two times, or we want to combine these imagery bands to create something that highlights vegetation for us. Those sorts of things are getting us towards making geospatial raster data just like any of our other data. And at that point, it will become mundane, boring, unsexy, all those sorts of things.
I just want to ask one final question here, but before I let you go, hey, if you were a geospatial professional today, or starting out your career again, and you had to choose a language. Now, I realize that you're a software engineer, you've been working with this for a long time, but if you had to choose a language, when you look around at things like RasterFrames, when you look at other initiatives out there, is there one particular language you would focus on?
Absolutely. I think it's Python, without a doubt. It's because, not because it's the best language in the world, but it has the best ecosystem in the world for this type of domain or any kind of analysis, frankly. R is sort of a second contender. We've thought about adding R support to RasterFrames, but we just haven't had the demand. I would say 95% of the touch points we have with RasterFrames, there are people who are understand Python or are comfortable with Python. And if you've used the first thing you would want to learn after Python is pandas, the sort of the natural data frame library, because Spark data frames are modeled after pandas data frames, and there's some interoperability between the two.
I really want to thank you for your time. I appreciate you starting us right at the beginning here and walking us through the environment that RasterFrames lives in, the functionality, the reasoning behind it, and perhaps what it's going to look like in future years. So I really appreciate it. You've really opened my eyes, and I think you presented some really interesting use cases for it. So before I let you go, if listeners are out there and they want to continue the conversation with you or reach out to you, where should they go to do that?
The RasterFrames is on GitHub, so you can find RasterFrames on GitHub. It's part of the Location Tech, Eclipse Foundation Location Tech organization. RasterFrames.io is our documentation. The company sponsoring it, my company, Astraea, is Astraea.earth. It's ASTRAEA.earth. Join us on Gitter. We have a Gitter channel for RasterFrames where we daily field questions and have dialogue about what RasterFrames can do and where it's heading. So we would love to engage with any and all who are interested in RasterFrames.
Thanks again. Really appreciate it.
Thank you. It's a pleasure.
So I really hope you enjoyed that episode with Simeon Fitch, the VP of Research and Development at a company called Australia. So I will be sure to put links in the show notes of this episode to Australia, to Raster Frames, and to Apache Spark, so you can easily find them. I just want to take a few seconds here to highlight a few of the things I found particularly interesting about this episode. And I think the first one was, so Raster Frames in itself is interesting. That's why, I decided to do an entire podcast episode around it. But also, I thought the particular use case or the particular functionality of chipping was incredibly interesting. Like the idea of producing a really, really big training data set, based on these chips, I thought was really interesting. And I'm pretty sure if people think long and hard about this, they'll come up with a million other things it could be used for. I also thought that Simeon was going to say SQL was the language of choice, that we as people working with geospatial data should be investing our time in SQL. But I was a little bit surprised to hear Python, not because I don't believe in it as a language, it's just because I feel like there's a movement towards SQL, and I see the utility of it, and I see as data gets bigger, we're storing it in a structured way. And for me anyway, I was just sure he was going to say SQL, but I understand why he chose Python, and his reasoning behind it, again, was not because it was the best language in the world, but because it was the best environment in the world. And I think that's probably pretty hard to argue with. I have just one last point I would like to try and highlight here. So towards the end of the conversation with Simeon, if you were listening closely, you might have noticed that we were talking about the future of this. What is Raster Frames going to look like in 5 years' time? And the answer was, I guess, not unsurprising, because the whole idea of Raster Frames is to make geospatial data, in particular imagery, a first-class citizen of the Apache Spark environment. So make imagery indistinguishable from other types of data. At this point, it just all becomes data. So in about this point in many conversations, when we talk about giving more people access to more geospatial stuff, we often hear the word democratizing. And if you've been listening to this podcast for a while now, you will have heard this word again and again, because lots of companies, lots of products, lots of services are seeking to democratize access to geospatial data, to geospatial functionality. So I have a couple of thoughts around this idea of democratizing geospatial data, geospatial functionality. And the first one is, I can't wait. So when the internet showed up and access to the internet was democratized, there was an explosion of creativity. And I don't think people could have imagined the kind of economies that would evolve around this democratization of access to a piece of infrastructure like the internet. I am pretty sure that 20 years ago, nobody imagined that people were going to be earning money, big money, on a platform called Instagram by posting photos of cats. But it's happening. I guess my point is here that when we give a lot of people access to this kind of infrastructure, that we have no clue what they're going to do with it. One thing is for sure though, if we allow people to contribute, they're going to contribute. If we ask them to participate and give them the tools, they will participate. So personally, I think this is going to be a really exciting time, and I am sure that we can look forward to a future with an extreme amount of creativity around this space. Okay, thank you so much for listening to my thoughts here at the end. Really appreciate it. I'll be back again next week with another episode of the Mapscaping podcast. I'd really appreciate it if you would join me then. As always, you're more than welcome to reach out to me for whatever reason. You can find me on Twitter and LinkedIn. You can also visit our website, mapscaping.com, and there's an email address. You can contact me there if you like. I would really love to hear from you. Okay, talk again next week. Bye.